Welcome to another exciting episode of AP Computer Science. Be sure to have writing utensils handy to take notes. A linked list is a sequence of elements arranged one after another, with each element connected to the next element by a link. The link to the element is combined with each element in a component called a node. A node is represented pictorially as a box with an element written inside of the box, and a link drawn as an arrow and used to connect one node to another. In addition to connecting two nodes, the links also place the nodes in a particular order. The 5 nodes form a chain with the first node linked to the second node linked to the third node, and so on until the last node is reached. The last node is a special case which is not linked to another node, and its link is indicated with a diagonal line. Each node contains 2 pieces of information, an element, and a reference to another node. This can be implemented as a Java class for a node using the instance variable to hold the element, and a second instance variable that is the reference to another node as follows. The declaration seems circular, and in some ways it is, but the compiler will allow such definitions. A list node will have 2 data members, an object and a reference to another list node. The instance variable will point to the next list node in a linked list. The list node class is constructed so that the elements of a list are objects. Since any class extends object, you can put any kind of object into a list, including arrays and strings. Whenever a program builds and manipulates a linked list, the nodes are accessed through one or more references to nodes. Typically, a program includes a reference to the first node and a reference to the last node. A program can create a linked list as showed. The first and last reference variables provide access to the first and last nodes of the list. This figure illustrates a linked list with a reference to the first node, where the list terminates at the final node indicated by a diagonal line in the reference field of the last node. Instead of a reference to another node, the final node contains a null reference. Recall that a node is a special Java constant that can be used for any reference variable that has nothing to refer to. There are several common situations where the null reference is used. When a reference variable is first declared and there is not yet an object for it to refer to, it can be given an initial value of a null reference. The null reference occurs in the linked part of the final node of a linked list. When a linked list does not yet have any nodes, a null reference is used for the first and last reference variable to indicate an empty list. Methods for a list node class will consist of those for creating, accessing, and modifying nodes. The constructor for the list node class is responsible for creating a node and initializing the 2 instance variables of a new node. Here's an example of code to create the first node in a linked list. After execution of the 2 statements, first refers to the header node of a small linked list that contains just one node with the integer 23. Getting and setting the data and the link of the node are accomplished with getter and setter methods as follows. The following segment of code using list node will illustrate the syntax of accessing the data members of a list node. In this section, we will look at a class that implements a linked list of linked node objects. This class encapsulates the list operations that maintain the links as the list is modified. To keep the class simple, we will implement only a singly linked list, and the list class will supply direct access only to the first list element. The singly linked list class holds a reference, first, to the first list node, or null if the list is completely empty. Access to the first node is provided by the getFirst method. If the list is empty, a no such element exception is thrown. Additional nodes are added to the head of the list with the addFirst method. When a new link is added to the list, it becomes the head of the list, and the link of the old list has become the next link. The statement list node value first invokes list node constructor. The line of code is broken down as follows. The new command allocates enough memory to store a list node. The new list node will be assigned the values of value and first. The address of this newly constructed list node is assigned to first. It's important to understand the old and new values of first. The very first time addFirst is called, the instance variable first will be null. A new node is constructed with the value and the null, and now first points to the new node. And the constructor provides a new node between the variable first and the node that first formerly referenced. Before the call of the constructor, first is passed as a null value. First is changed, references to the newly constructed node. The second time that addFirst is called, the first is already pointing to the first node of the linked list. When the constructor is called, the new node is constructed and placed between the first and the node first used to point to. The value of first passed to the list node constructor is used to initialize the next field of new node. To traverse a list means to start at one end and visit all the nodes. In the case of method printList, the task is to print the value field from each node. We need a variable to traverse through the list, so temp is created. Because temp is an alias to the first, we can use it to traverse without altering the reference to the start of the list. The list node variable temp will contain null when we are done. Until temp equals null, the while loop will do 2 steps at each node. Print the data field, then advance the temp reference. The statement temp equals temp.getNext is a very important one and moves the temp to the next node. A linked list must end with a null value. Without such a marker at the end of the list, a routine cannot see the end of a data structure. This assignment of null value at the end of the list is often taken care of when a new node is packaged or through the use of a constructor. When a reference variable is null, the programming error to invoke one of its methods or to try to access one of its from the instance variable. For example, a program may contain a reference to the first node of a linked list as follows. Initially, the list is empty and first is the null reference. At this point, it is a programming error to invoke one of first methods. The error would occur as a null pointer exception. If data are supplied in unordered fashion, building an ordered linked list from the data becomes a harder problem. Consider the following cases for inserting a new value into a linked list. Insert a new value into an empty list. Insert the new value at the front of the list. Insert a new value at the end of the list. Insert a new value between 2 nodes. The resulting ordered linked list would look like this. 2 of the cases are easy to identify and solve. The empty list case, and placing the new value in front of the list. Adding a value to the end of the list is easy to identify and solve if you maintain a marker to the last node. To assist us in our discussion of linked algorithms, 2 definitions will be helpful. An internal pointer is one that exists inside a node. An internal pointer joins one node to the next in the linked list. An external pointer is one that points to a node from outside the list. Every linked data structure must have at least one external pointer that allows access to the data structure. The linked list in this lesson has 2 external pointers, first and last. Suppose a 5th value, 61, is to be inserted into the list. We can see in the diagram that it will go between 42 and 95. When inserting a value into a list, we will use helping external pointers, also called auxiliary pointers. It is possible to find the attached point using just one auxiliary pointer, but we will use 2, temp and back. Using 2 external pointers makes the hookup easier. Finding the attachment point involves a search. The pointer temp starts at first and is moved through the list until it is just past the insertion point. The pointer back trails the temp by 1 position at each step of the search. This is the position of our pointers at the end of the search. The new node needs to be placed between back and temp. If we call this new node new value, then inserting it into the list will consist of the following steps. Searching an ordered linked list is a sequential search process similar to what we just covered with insertion. A linked list is not a random access data structure. You cannot jump to the middle of a linked list. Only sequential moves are possible. The search function could return a value or a pointer to that cell. Deleting a value involves the following steps. Locating the value, if it exists, to be deleted. Rehooking the pointers around the node to be deleted. Updating the first or last if necessary. A node of a doubly linked list will contain the information field in 2 reference fields. One reference will refer to the previous node, while the other reference will refer to the next node in the list. The following class definitions will be used. This illustrates a doubly linked list of type D list node containing integer objects. A null value must be placed at each end of the list to signify the end of the data structure. In the diagram, a null is indicated with a diagonal line. A doubly linked list should have 2 external references to access the data structure. In each case above, first and last are the 2 entry points. A doubly linked list contains first in either direction. Inserting values into an ordered doubly linked list is a similar process to the algorithm used with a singularly linked list. However, the number of reference manipulations will double. The addition of a new node to a position between two existing nodes will require 4 reference hookups. Thanks for hanging on to the end of this video. See you next time.